Okay, so I've pressed record, so hopefully that should be working now. Okay, so okay, whew, let me get let's get restarted. So Miss has introduced the do now to you, so hopefully you started to have a little think about that. Hopefully you're starting to write a bit of an answer. What I'm going to do now is I'm going to share for you my iPad screen, which is where I'm going to be able to work on the question with you, which is going to mean that we can be a bit of collaborative and you can see exactly how I would tackle this question if it were me in an exam. Obviously, I'm many years past that now, but if I were going to do it, okay? So if you're still writing, please do continue. But the first thing that I would do, like Miss said, is think about what this question is actually saying. So we can see here that the question clearly says, state the effect that increasing temperature has on the rate of reaction. And ultimately, year 10, it doesn't matter what reaction we're talking about here. When you see those two things together, then you know what you're going to be talking about. And you're going to be talking about collision theory. Now, in the question, it also says, make sure that you talk about this in terms of particles and in terms of collisions. Now, I've seen a really good answer in the Q&A already. But what I'm going to do is I'm going to take you through the really key things that you will need to include in this. And then in a little bit, we'll start to open it up to polls, etc. So hopefully in your answer, the first thing that you talked about was the idea that by increasing temperature, you increase the kinetic energy store of the particles. And I apologize if my handwriting's a bit skewy. Now, when you increase the kinetic energy store of those particles, what's going to end up happening is those particles are going to move more. And when they move more, then you're going to have an increased frequency. And it's important that we use that word frequency. Oh God, this is where my spelling sort of goes a bit funny. Frequency of collisions. And because we're talking about temperature, year 10, not just increased frequency of collisions, but more energetic collisions as well. So more energy in the collisions themselves. Now, if you have more frequent collisions and more energetic collisions, then you're going to have more particles at or above the activation energy, and so you're going to have a faster rate of reaction, or an increased rate of reaction. Now, I just want to say one thing about this question. I've marked some from my other classes, and one thing that a couple of people said is that you would have a less reaction time, or you'd have more reaction time or increased reaction time. Be very careful, okay? Be careful about talking about reaction time versus rate of reaction, okay, guys? Because reaction time, when you start to talk about increased reaction time, that's actually longer, okay? So it's kind of the opposite of what you mean. From what I could see in the Q&A, that was great. And what was really good is that so many of you were talking about both the idea of energy and collisions and increased frequency of collisions. Mrs. Bush, can you now just see my slide?
I can just see your iPad, Miss.
Oh, okay, that's absolutely fine. So what I'm going to do now is re-share the presentation itself, and we're going to move on. So today, year 10, we are going to talk about a particular type of change that happens in a chemical reaction. Now, next week's webinar, we're going to go into some real tough, higher content. You're totally capable of it. But what I want to do this week is build up to that. Make sure that we fully understand some of the stuff that we did last year, and also move us into some new content. But in order for me to do that, I need to see how we're doing so far. So the first thing I'd like us to do is to have a go at this poll. So, if I can remember how to do my polls. Honestly, Miss, I've completely forgotten how to find my poll. Okay, bear with me.
Have you found it, Miss? It's at the top, and then it should say poll. It's where it says screen share. It should say polling, and then launch poll.
It does not.
Oh, weird. Hang on.
Yeah, very
Oh,
strange.
can I might be able to launch it for you. I
You're
think
the host.
I'm in first. Quite obviously. So, poll 1, what are the signs of a chemical reaction? Is that it, miss?
Yes, please, miss. So,
I
guys,
have launched that poll for you.
brilliant. Have a go at the poll. I want you to tick all that apply. So, what are the signs that a chemical reaction is taking place? And what we're going to do after you've had a go at this is we are going to focus in on one type of change. So you can tick all that apply. You've got about 30 seconds now because it's not the most difficult of questions. Off you go. How are we doing, Miss? How many people have responded to the poll? I can't see any of that.
We are doing really well. We've got 60% so far, and it's been
Excellent.
on for 45 seconds. So I guess if we give it just another 15 and then it'll be on for a minute, and people will do well. I'll end it in 10 seconds. We're doing really well.
Excellent stuff.
It's worth saying at this point, isn't it, Miss, that there's no point that at no point do we see who's answering this. So it's all thing.
Yeah, it's all anonymous. So I'm sorry, Miss Bishop, I've just nicked the host back off of you so that so that I can control it. It's a bit easier. So well done to everybody who has answered this, and I am particularly impressed that the answers that are all really big signifiers of a chemical reaction are the ones that are the most popular answers. So light is given out. Absolutely, you can get phosphorescent and fluorescent reactions. Magnesium burning is one. You get that really bright light. Bubbling and fizzing, yes, that means a gas has been produced. Temperature changes, we're going to look in more detail about those two in a second. Colour change, we know, we've seen it before in many reactions. And the last one, I kind of threw in there as a bit of a talking point. So states of matter changing. Now, that isn't always a sign of a chemical reaction, because if I boil water, there's a state of matter change there from liquid to gas, but I'm not actually physically changing the chemical component. So it's not a chemical reaction. So it might give you a hint that something is happening, but it's not a full-on way to show that a chemical reaction is occurring. So what we're going to do now is we're going to move on and we're going to talk specifically about temperature changes in reactions. Now, it is important to note that I know you have covered this content before, but what I also know is this was in year 9. And in order to move on to what we're going to next week, we need to have a firm and full understanding of temperature changes in reactions and what that means in terms of energy. Now remember, you don't have to take notes of anything we're going to do because the slides and this video will be available for you to reflect on. Later on in this video, I am going to ask you to have a go at some stuff on the paper that I've asked you to bring with you today. So first of all, we know that in a reaction, we can see a temperature increase and we can see a temperature decrease. Both of those things tell us that a chemical reaction is taking place. Now, reactions where that temperature increases is known as an exothermic reaction. Now, exo and thermic. Thermic, heat. So as soon as you hear exothermic and endothermic, what we should be thinking about is heat. Exothermic is heat exiting the system. So it's where heat is released into your surroundings and the temperature increases. And that makes sense. To help with your memory, I've tried to always put exothermic in a red box so you can think about it as a temperature rise. An endothermic reaction is the opposite of that. So it's where the temperature decreases in a reaction. And that's due to energy being absorbed into the chemical bonds themselves. So energy is absorbed from the surroundings, which make the surroundings cool down. And that's what we measure temperature of. Now, I'm going to go through the detail here with you, and we're going to stop and test and see how we're doing as we go. But it's important that if you have questions, you can either write them in the Q&A or wait till the end and put your hand up. But hopefully, we'll cover it as we go. So let's have a little look at the second poll that we're going to do today. And this poll is I want you to decide whether each of the 4 reactions that you see that I've described are exo or endothermic, depending on what I've just said. So you've got 4 there. So a reaction began at room temperature. After 10 minutes, the temperature had risen to 32 degrees. Is it endo or exothermic? And so on and so forth. I want you all to have a go at this. And again, I have no idea who's answering what. Okay, so let's have a look. Is the temperature increasing or decreasing? Does that mean heat is being given out to the surroundings, exothermic? Or does that mean heat is being absorbed from the surroundings and it getting colder, which would be endothermic? So I've got 2 people. Oh, I've got some differences of opinion. So a really good question. Somebody's asked me what room temperature is. Now, guys, room temperature is between 20 to 25 degrees. Okay, normally in an exam they give it to you, but it's important just to be aware of whereabouts that is. But that's an excellent question. Okay, just having a little look through because I have the wonderful opportunity to have a look at some of the answers as they're coming in. I'm going to give you a little bit longer on this poll than that we did on that first poll, because I really want you to go through each of them. Now, in the exam, these are dead easy questions. They're tick box questions. They're quick answers. Okay, I'm going to give you 30 seconds, and that will bring you up to 2 minutes on this poll, and then we will go through the answers. Okay, just 5 seconds left. If you are thinking about what you're going to vote for, then just pop it in now. Okay, so let's share the results on this and let's talk through these examples. So this first one, a reaction began at room temperature. After 10 minutes, the temperature had risen to 32 degrees. That would make it an exothermic reaction. Okay, exothermic, temperature rises. It gets warmer because heat is exiting the system, which is the chemical bonds that were there, okay? So heat is being given out. Number 2, reaction started at 20 degrees. After a minute, it had reached 22. It is, in fact, an exothermic reaction, okay? It's only slightly exothermic, but actually we only measured it for a minute. So chances are the temperature would continue to rise afterwards, okay? But it is, in fact, an exothermic reaction. Well done to most of you there. The third one, a reaction reached completion at a temperature of 12 degrees. That means on that graph we looked at for rate of reaction, at the very end, it was 12 degrees. But it began at room temperature. Is this reaction endothermic or exothermic? It is an endothermic reaction. Heat has been absorbed from the surroundings to make the reaction happen, which means the surroundings have cooled down. Lastly, a student was investigating how 2 compounds reacted. She needed to heat them strongly throughout the reaction. Is this reaction endothermic or exothermic? Now, Yatin, I put this one in there because this is one where it tends to be the one that people struggle with the idea of. Now, let's think about what exo and endothermic mean. Exothermic means heat is given out in the progress of a reaction. Endothermic means heat needs to be absorbed for the process of the reaction to take place. So therefore, if it's a reaction that you need to heat strongly to make it happen, or you need to heat it at all to make it happen throughout the reaction, then it is in fact an endothermic reaction. And so that's a nice and good way of being able to remember about endo and exo, because endo will need to absorb some heat from around it. Now, a really good question that somebody has just said in the Q&A is, if the heat has moved to the surroundings, doesn't that mean the reaction would cool down? Now, this is where we need to think about the energy levels themselves. So if you can hold that thought, when I show you the next couple of slides, I will then try and explain what that actually means, because I take your point, this does seem a bit confusing at the moment. So what I'm going to do now is I'm going to go through the 2 types of reactions, and I really want you to focus on the language I'm using here. When I talk about energy and when I talk about temperature, I mean different things. Energy and heat is how much energy is stored. Temperature is how much the temperature rises. So, what is an exothermic reaction? Okay, so in an exothermic reaction, the amount of energy stored in the chemical bonds of the products, that's the stuff that's made, is lower than that of the reactants. So in the reactants, the stuff that you react together, the energy stored in their bonds is more than the products they make at the end. Now, because this energy here is more than the stuff they made at the end, that energy's got to go somewhere, okay? We don't destroy energy. You hopefully know that we never create or destroy energy. It simply is transferred from one store to another. So in this case, because the energy level of the products, the stuff you make at the end, is lower, energy is given out to the environment as heat. And that's what you measure. That increases the temperature. When you've got your thermometer in a reaction, you're measuring the amount of energy in the surroundings. Your thermometer can't measure the energy in the bonds. So when you measure temperature, you're measuring the energy of the surroundings. So exothermic, let's look at that in a graph, because in your exam, you will have to recognize these graphs. So this is the energy profile for an exothermic reaction. As I've said, and we'll look at this one on the left first, the reactants here are at a higher energy level than the products. That means within their bonds, there is more energy stored than in the bonds of the products that they make. Now, in a chemical reaction, what happens is when things react, what initially happens is the bonds break up in the reactant and then they reform the products. Now, in C1, you did bond energies. We don't have time to go through that in more detail now, but it is important that you can remember that. So if you can't, it might well be something that you decide to look back on in your own time. And bond energies helps to understand exactly why things are exo or endothermic. So this graph, you have reactants at a higher energy level than the products. And you can see that there is this drop in the amount of stored chemical energy. And that energy has got to go somewhere. And in exothermic reactions, that energy is released into the surroundings as heat. And so the temperature increases. Now, on the right-hand side, I've given you a slightly more technical diagram. I've given you a diagram that has slightly more detail. And I was going to do a poll here, but I want to keep going so we can have some time to practice this. But on this diagram, you can see that there is a little hump. There is a little hump to get us going. Quickly in the Q&A, can anybody really quickly tell me what that little bump is and why it's better to have it on there than just this flat diagram? We did this last time. So on an energy profile, brilliant, 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 brilliant. Well done to all of those people who have just come through. You're absolutely right. In an energy profile, even though the products are at a lower energy level than the reactants, I have to give the reactants a little bit of energy to get the reaction going. And that energy kind of breaks the bonds up, okay? And that is known as the activation energy. Now, in a bit, I'm going to show you an exam question about these graphs because there's loads of questions about them and they're really easy. But you need to be able to label that. So the amount of activation energy is the distance from here to the top of the bump, if you like, okay? So as A and B turn into C during the reaction, overall, the energy level decreases of the energy stored in the chemical bonds, and the energy that's the difference between the reactants and products is the amount of energy that's released to the surroundings as heat. But you do have to stick a little bit of energy in there just to get it going, okay? So that's the activation energy. So that's an exothermic reaction. So hopefully that explains it a little bit. Now, the next one, before we go on to endothermic reactions, let's look at some examples. So Yes, that's right. Exothermic, increase in temperature. And some examples here are, well, exothermic reactions are quite easy to think of examples. Anything that there's a fire burning, okay? Because that fire, that heat being given out in combustion is just a sign that it's an exothermic reaction. And I've put these on here because these are the, you know, the most safe, I suppose, way of showing an exothermic reaction. And those are hand warmers, okay? There's a little thing that you click in there and that little spark makes a reaction, a chemical reaction take place. It triggers the chemical reaction. And then what you have is an exothermic chemical reaction that gives out heat and that keeps your hand warm in the winter, okay? Now that's actually a reversible reaction. Those of you that have got hand warmers know that if you put them in a pot and you heat them up, you can get them back to where they started. Now we're going to talk about that at the end of this webinar, but also in the next one. So it's an important point. Now let's look at endothermic reactions. So we're in blue because we know that we're talking about a temperature decrease here, but that's a description. So just saying the temperature goes down is just describing what an endothermic reaction is. What we need to do is to be able to explain what an endothermic reaction is. So it's the opposite of exothermic. And if you're struggling with, if you struggle naturally to remember large volumes of information, it's the opposite of exothermic. So remember one and apply it exactly the opposite way to the other one. So in this case, the amount of energy stored in the chemical bonds of the product is higher than the reactants. So the chemical bonds of the stuff that you react together to make the product is at a lower energy level than the stuff that you actually make. Okay, that's at a higher energy level. Now, in order to make that jump, that energy to get up to the product, that's got to come from somewhere. And so that energy needs to be absorbed from the surroundings. And that means the surroundings themselves, they cool down. Okay. Now that means that overall the temperature is going to decrease because energy has been absorbed into the chemical bonds to form those new bonds in the product. Now again, I think the easiest way to memorize this is to look at the graphs themselves. So quite the opposite way, like I said, this is an endothermic reaction. You have your products at a higher energy level than your reactants. This difference here is the total amount of energy that's absorbed in the reaction. And just like with exothermic, you can also draw the activation energy at the top here. So the reactants absorb heat from the surroundings to make the products, okay? So heat is absorbed from the surroundings to make the product. Now, when we say that the energy store is higher in endothermic, not in general, we're not saying that endothermic reactions have more energy than exothermic, okay? They're the same. What we're saying is that in endothermic reactions, that the products, the stuff you make at the end, has a higher energy level than the stuff you begin with. So in your reaction, the chemical energy stored in the bonds of the stuff you begin with is less than the chemical energy that is stored in the products. And so in order to make those products, you need to absorb energy. And that's why I said earlier that any reaction that you have to give heat to continuously to make the reaction happen, that is an endothermic reaction because it needs to absorb that energy in there. And like I said before, you can draw it with an activation energy. Okay, so this bump here, that's an activation energy to get it going again and bring it down to the products. Okay, so examples of endothermic reactions. There are two ways you can think about this. Does the temperature decrease? If you don't heat it, if there's no heat involved, but the temperature is decreasing, it's endothermic. So looking here at the cold pack, when you get those cold packs, I'm not sure if they have them in the medical room, that you can sort of break and they cool down really rapidly. That's because what you're doing is you're breaking a barrier between two chemicals that causes them to react together, that causes an endothermic reaction to take place, which means that it brings in all the heat that was stored in there normally into the chemical bonds, and so it cools down. And so that's one way of thinking about an endothermic reaction, that it cools down. The other way of thinking about it in terms of examples are, what reactions do you have to give energy to make them happen? Well, let's look at this diagram here. Cooking are endothermic reactions, okay? I can leave my bread mixture on the side, but it ain't gonna cook, okay? It ain't gonna cook as long as I leave it. And that's because it's an endothermic reaction that's taking place, okay? It needs me to give it energy. It needs to absorb energy in order to happen, in order for those products to be made, the lovely fluffy bread, the carbon dioxide to be released to give the air holes in the bread, okay? Photosynthesis, that's how plants make their own food, but they do it using the sunlight, okay? They do it using the energy from the sun. Photosynthesis doesn't take place at night because it doesn't have that energy, okay? So anything that requires energy to be absorbed to take place, that is endothermic. Now, I know I'm talking around this a lot, okay? And I'm giving you lots of detail, and I'm not surprised if you're starting to get confused between the two. So let's really be clear on the differences. This is an image of the graphs for both side by side. And hopefully, oh, let me go back. Hopefully you can see what we're talking about. So endothermic reactions, first of all, in your head, endothermic, it cools down, temperature decreases. Why? Well, that's because in an endothermic reaction, the reactants are at a lower energy level than the products. This means they need to absorb energy from the surroundings in order for the reaction to progress. When you absorb energy from the surroundings, the temperature of the surroundings is going to decrease, and therefore the reaction is going to cool down, okay? So that is an endothermic reaction. Exothermic is the opposite. In an exothermic reaction, the temperature increases. Now, the reason the temperature of the surroundings or the temperature of the reaction vessel increases is because the reactants are at a higher energy level than the products. As the reaction progresses and the products are formed, the excess energy from the reactants that's not being used to make the products is given out to the surroundings. It's released to the surroundings. This causes the heat store of the surroundings to increase, and therefore the temperature of the surroundings to go up. So really simply, endothermic, you cool down. Exothermic, you heat up. And a really simple diagram to show you this is here. An exothermic reaction, heat is given out and it gets hotter. An endothermic reaction, heat is absorbed, heat energy is absorbed, and it gets cooler. So that's it really, really simply. Now, what I want to show you are two examples of really, really simple questions on this. Now, the first one, the reaction between sodium and chlorine is an exothermic reaction. So in your head, what are you thinking when you hear exothermic? What is that word? What are the words that you're thinking of straight away? You should be thinking increase in temperature or hotter. It gets hotter. It says complete the reaction profile for the reaction between sodium and chlorine. Now here, they give you a line for reactants. Now, if it's an exothermic reaction, the products are going to be lower. And then you need to think about how you draw the line. And I'm going to show you in just a second, but I wanted to show you another question, which is actually a little bit less kind than the first one. And this is the one we're going to look at together. So guys, if you've got a pen with you and some paper, what I want you to do is to have a go at this question. And I'm going to show you in a second together how it's done. So it says, draw a reaction profile for an exothermic reaction using the axes in figure 1. So they give you those in the exam, okay, but they're really simple. It says, show the relative energies of reactants and products and activation energy and overall energy change. So those two things are things you need to label. Now, whilst you're having a go at that, I'm going to do it at the same time. And I'm going to label it as how you would need to label it in an exam to get those full marks. Okay? So off you go, guys. I want you to draw me a reaction profile from the top of your head, just on a bit of paper that you've got or anything that you've got that you can write on, and have a go at that. Whilst you do that, I'm going to share my screen down here, which will hopefully help you if you get stuck. So you should be doing this yourself, ladies and gents. Okay, so have a look here. So it says draw a reaction profile for an exothermic reaction. So I'm just going to make sure I've got that highlighted there. I can do this in my exam as well. There's no issue with that. I'm going to start now drawing my relative energies of my reactants and products. Now it's an exothermic reaction, which means my reactants should be higher. So I'm going to write reactants on there. I'm actually just going to zoom in slightly, guys, so that I can draw it a little bit better. I am then going to make sure my products are drawn lower. Now, ladies and gents, hopefully you're realizing this isn't completely as accurate and as neat as the diagrams I showed you, but that's fine because you don't have a computer in the exam, so they're going to be different. So that is the first part of the question done. Second part of the question, activation energy and overall energy change. So I know I need to draw a line from up here to down at the products. So let's draw that line with the activation energy. So we go up and then we come down. Okay, now that is an appallingly drawn line, but it gets the point. What I then need to do is to make sure I've labeled the activation energy. So I'm going to draw a little line there. I'm going to show that this is the activation energy because that's the amount of energy you need to put in order to get the reaction going. It's the amount of energy above the reactants here. And then I'm going to label the overall energy change for the reaction, which is from the reactants to the products. It ignores the activation energy because that's just to get it started. The overall energy change is the line from reactants to products. Now, that, ladies and gentlemen, is a 3-mark question. Okay, and hopefully you had something very similar to this, possibly a lot neater. Okay, now here you can see that you get 1 mark for simply saying that reactants and products are at those 2 different levels. Okay, your second mark is for the labeling of your activation energy and making sure that you draw the bump. Okay, if you draw the bump and don't label activation energy, you may get a mark. And the overall temperature change is from the reactants to the products here, okay? Now, someone is saying, is this change in temperature part of the actual chemical reaction or just the surroundings? Well, if you imagine, here's where I'm going to sort of find a nice blank space on here. So if you imagine that in your reaction vessel here, so that's your beaker, apologies for, again, poor drawing. Inside there, if you zoom right in, you've got the individual chemical bonds here, okay? Now, as a reaction takes place, these are going to break. They're going to sort of live as these sort of weird transition complexes, and they're going to form something new, okay? So you might form something completely new here, okay? Now, as they do that, in an exothermic reaction, the energy in these bonds here, oh God, that's not an arrow. The energy in those bonds is less than the energy in the bonds to begin with. And that's why energy, as this does this process, breaks the bonds and forms something new, it's going to have a release in energy because it takes less energy to form the new bonds. And that release of energy, if I scroll out, is going to be given out as heat energy, okay? Now, when I stick my thermometer into the reaction vessel here, and when I say reaction vessel, guys, it just means anything. It can mean beaker, it can mean cup, anything. But this is my bad thermometer drawing. When I measure temperature in here, okay, I'm not measuring the energy level of the specific compounds because I can't do that. That's not what a thermometer does. it will measure how hot the surroundings are getting. And when I say surroundings, I don't just mean out here. I actually mean in between the molecules themselves as well. So the surroundings here, we could be talking about this actual vessel heating up itself, okay? Because that's how we measure it. We measure how hot this is in here, because the energy is being released from the bonds to the space around the bonds. So that is a mess, but I hope it explains a little bit better. Now, when I've looked into the exam questions on this, these questions come up with this graph here again and again and again, and they are easy because they're 3 or 4 marks, sometimes 2 marks if they're only asking you to do a couple of things. And the really important thing that you remember, like I've said, is where is activation energy? What is the overall temperature change? And have you got these 2 things in the right direction? If this was an endothermic one, then you would have the opposite layout, okay? You would have reactants down here. Let me try and make this bigger for you. You would have products up here. You would have the reaction line. You would have activation energy here. And you would have the overall, put a little dot line there, overall temperature change here. Okay, now exothermic is the more common one that you'll be asked about in the exam, but endothermic obviously will come up possibly as well. So that is just a really typical question about exo and endothermic reactions. Now, what I'm going to do now is go back to the screen sharing, and I'm going to go through with you the sort of next part of what we're going to do. Now, just very quickly on exo and endothermic reactions, you do have questions that come up that say things like define an exothermic reaction. And really simply, guys, it's a reaction where the temperature increases because energy is being released to the surroundings. Endothermic, it's a reaction where temperature decreases because energy is being absorbed from the surroundings, okay? They're quite short questions and quite short answers as well, okay? But normally they're involved in other topics as well, which is what we're going to see moving on. Now, what we're going to go through now, and I've left that question in there if we had time, is we're going to look at reversible reactions. Now, this is something that some of you will have done in lessons, and this before we went into lockdown, and this is something we're going to build upon next time. And so I've put this in here now so that you can begin to think about it. You can do some work over the next week, so that when we come back next Monday, I can move on to something a little bit more tricky and you will be aware of it. Now, a reversible reaction is one where you can make the products, but you can also go back the other way and make the reactants again from your products. The way that we show this is with this setup here. So we have A plus B, we have a reversible sign. This shows you that the reaction is reversible, goes to C plus D. Now that means in certain conditions, if I react chemical A and chemical B together, I'm going to get chemical C and chemical D. But I can also have chemical C and D reacting together to make A and B again. And that will often require different conditions. And a lot of the time, it's actually quite annoying for chemists because it means when they're trying to make their products, you've got a little bit of a backward reaction happening at the same time. Now, in terms of the way in which we need to be naming this symbol, these are 2 half arrowheads, and that shows you that the reaction can happen one way, and it can show you that the reaction can happen back the other way. And interestingly, it also shows you that these reactions can happen at the same time. So whilst you're making C and D, you could also be making A and B again. Now, the forward reaction is the one that we say goes toward the right. Okay, so when we talk about forward reaction, we're talking about the one that goes as you would read it. The reverse, or the backward reaction, is exactly that. It's against the way that we would normally read it. Now, people have asked me, this is brilliant, you're queuing me up perfectly, year 10. What is an example of a reversible reaction? Well, we've got 2 here, and ideally I'd show you them, and if I can get this stuff together, I will have a go at one in school and release a video for next time, but you can find these videos online. So the first example of a reversible reaction that the exam board says you should be aware of is the reaction of ammonium chloride. So ammonium chloride is this white solid that's just below my face here, and it's pretty nothing when you look at it, okay? Now, what happens when you heat it is it breaks down, it decomposes, and it forms ammonia and hydrogen chloride. And those two are gases. So you go from this solid, you heat this white solid, and you create these gases. Now, when the gases are cool enough, they actually react together to form this white powder again. So by heating it up, it breaks down, I form my products, allowing it to cool down though, and they're going to come back to the same reactant again. And that reversible reaction is shown here. So ammonium chloride breaks down to give you ammonia and hydrogen chloride. And the other way is ammonia plus hydrogen chloride gives you ammonium chloride. Now, there is a change of state in this reaction, but it's not just a change of state. This is a chemical reaction that's happened. The NH4Cl has broken down into two new compounds. Now, I like this one because it really shows you how changing the reaction conditions is going to change the products you make. So, the forward reaction, and this is a tricky one. Do you think that is an endo or an exothermic reaction, Year 10? So the forward reaction, based on what the description is on the board. Pop an answer in the Q&A anonymously if you want to. I'd like to see your name, but anonymously is fine too. So looking at what the description says, ammonium chloride is a white solid. It breaks down when heated, forming ammonia and hydrogen chloride. So is that exothermic, where heat is given out, or is that endothermic, where heat is absorbed? Really think about this, guys. Just because it says heat, it's not exo. Okay, good, well done. I've got lots of people who are giving me really good answers there. Okay, well done, good, excellent. Sorry, I'm getting lots of really good answers. Brilliant, Year 10. So I know some of you have said exo because you saw the word heat, and I get it completely. But this is an endothermic reaction because heat is absorbed. Okay, now interestingly enough though, if it's endothermic one way, it's going to be exothermic the other way. So when ammonium chloride breaks down to form ammonia and hydrogen chloride, that's endothermic because I've got to heat it up. But the reaction of the two gases to form ammonium chloride, that's exothermic. That gives out a little bit of heat. Let's look at another example. This is one of my favourite reactions to do in the lab because it's really obvious, and I'll try and get it set up for you next week. Hydrated copper sulphate is this beautiful blue compound, okay? It's this blue solid, really bright. And if I heat it, what happens is I change the hydrated complex and I separate the copper sulphate from the water molecules. And I get this, which is anhydrous copper sulphate and steam. And anhydrous copper sulphate is a white powder. So I heat hydrated copper sulphate up in an endothermic reaction, and I get anhydrous copper sulphate, which is white. That's endothermic because the hydrated copper sulphate needs to absorb heat in order to react. But when you leave it and it's cooled down, anhydrous copper sulphate will react with the water in the air to form hydrated copper sulphate again. And that reaction is exothermic in that it generates and releases some heat. So that's a really important thing that we need to remember. And it's important because next webinar, next lesson, we're going to be talking about something called Le Chatelier's principle. And Le Chatelier's principle is a higher content, piece of higher content, which isn't overly difficult, but it can be difficult to get your head around straight away. But this is what we need to be thinking about. Energy changes in reversible reactions. If a reaction is exothermic in one direction, it will be endothermic in the other. The exact same amount of energy is transferred in both reactions. So if it's endothermic one way, so if we're looking at here and it has to absorb some energy to make the copper sulphate, well, that amount of energy it absorbs is the exact same amount of energy that it will release when it forms back the other way again. Okay, so the energy changes are exactly the same, but they're in opposite directions. And so one way it's absorbed and one way it's released. Now, equilibrium, I'm going to very quickly introduce this before we look at something else. Equilibrium is when the rate of the forward reaction, A plus B gives you C and D, is equal to the rate of the reverse reaction. So C and D reacting to give you A and B. And that's when those two things are reacting together A and B and C and D, and you're getting an equal rate of reaction in both directions, okay? That means the rate at which A and B is formed is the same as the rate at which C and D is formed. And that only takes place in a closed system, and that's where you've got a lid on it, basically, okay? If you don't allow anything to escape, you can reach equilibrium. And equilibrium, guys, is a word that just means balance, okay? So that's where it reaches this sort of balance. Now, this is all here on the slides, and I've just added that on there so that you could see it as well. There are some questions, but we're running out of time, and I don't want to get cut off again this week, okay? So let's just quickly recap. We have done exothermic and endothermic reactions today. Endothermic, heat is absorbed because the products are at a higher energy level, which means the temperature goes down. Exothermic, heat is released because the products are at a lower energy level, which means the temperature increases. A reversible reaction is one where you both make the products and the products themselves can react to make the reactant again. Equilibrium is where the rate of the forward reaction is the same as the rate of the backward reaction. And the rate means how quickly they're happening. And that can only happen in a system that is closed, i.e. nothing can escape. So the work that you've got to do this week, Year 10, you've got a quiz to do, as you always do, and then you've got a series of questions to have a go at. And there are some additional videos from Miss Yarby. The questions are not overly long in terms of their answers, and that shows you the sorts of questions you will be asked on this topic. As always, this webinar is being recorded and you will be able to watch it on YouTube once it's been uploaded. And please do, specifically if you can't remember those explanations, okay? So unless anyone's got any questions, you are now free to go and to continue with the rest of your day. If you do have any questions, I am happy to stay for the next sort of 3 minutes until the next webinar starts, and then answer those. And if not, you can sort of go. And there is a drop-in clinic later on in the week to support you with your learning if you have any questions that arise then. Somebody's asked me, are chemistry questions usually less marks than biology? No, they will normally have around the same spread of marks, but different topics within chemistry will normally be worth different numbers of marks. So for example, you normally get 4-mark questions about rates of reaction. Unless it's about a specific experiment, then they tend to go up to 6 marks. If they're maths-based questions, they're normally capped at 3 or 4. So it's just about looking at the different topics. You absolutely can access this after. I totally get it. You know, hearing me rambling on for nigh on 50 minutes is hard. It will be on the Science YouTube channel. It should be linked in your Google Classroom. If it's not, please ask your teacher to link it for you or to send you a link to the YouTube video itself. It should be available by tomorrow morning. Like I said, guys, if you don't have any more questions, please do feel free to leave. I'm just going to hang on for about 2 minutes just to make sure there isn't anybody with an urgent question. And thank you for coming as well and putting up with my tech issues again. But we got them fixed quicker this time.